Good everyone, Moyin.dev AI. Today we'll be taking a quick look at a project we just recently worked on in our ongoing AI and Data Science Bootcamp. So yes, this was the project to round up our Python side of learning. So this is like a final project just to test the ability of students. And today I'll just be walking you all through the correction we made for it and how we were able to solve it. Yeah. So the assignment was to incorporate a traditional logarithm calculator into a set of calculator functions. So instead of using the normal logarithm module to make this work, wanted to traditionally code it out. So that's what we worked on here. So yes, firstly, at least on my side, for every task I get, for every script I'm asked to write, one thing I always love to do is to research. Right, so close the laptop for a while, make some research. How exactly would I be solving this without a laptop? So what's the manual way to actually address this problem? What's the proper way to address the problem? Then you write an algorithm of that. I usually use my pen and paper a lot when I code. So write down an algorithm of that and then translate that algorithm into code. So yeah, that's how I like to work. So for these, first went into research and I was able to piece together the traditional and one of the methods by which logarithms were calculated traditionally. I'm sure this takes us back to, I don't know if I was the one that experienced it, but back then my dad would always tell me about when he was in school and there were no logarithm tables and calculators. They used to calculate logarithm from their head, and then yeah, it was one of the interesting stories I had back then. So this really took me back as I was able to research how exactly logarithms were gotten back then very accurately. So yeah, through this project, I'll just take us first through the research, how it is done manually, then we'll bring that into a code world. Yeah, so very quick, very simple, not to waste our time. Yeah, let's get into it. So first, overview. This program calculates logarithm in base 10 using traditional method that mimics how logarithm tables were originally constructed in the 17th and 19th centuries before calculators existed. So yes, first, let's understand logarithms. Let's actually understand the concepts behind logarithms. What are they? Logarithms, as we've written here, log base 10x. What exactly is that? It answers a simple question, a singular question. What power do I raise 10 to get x? Let me go again. Logarithms answer a question. What power do I raise 10 to get x? Note, 10 here is the base, right? So we have logarithm in base 10. So 10 is the base. What power do I raise the base to get x? That's simply what logarithms are at their core. So a few examples here. We have log 10 of 100, 2, because 10 is to the power 2 will give you 100. We have log 10 of 1000, 3, because 10 is to the power 3 will give you 1000. And then we have log 10, log base 10, right, of 2. And that approximates into 0.301. Why? Because 10 raised to the power of 0.301 will give you 2. So we see the interplay, we see the interchange in here. And if you remember calculus from back then when you were in secondary school, even through university, the earlier stages of university, for those that did maths, you'll be able to get this concept and understand it properly better. So yeah, but let's take things a little bit deeper. Oh, sorry. Let me just zoom in here to make sure we are seeing this properly. Yeah, so let's take this a little bit deeper. Let's analyze it a bit further. Logarithms have two parts, right? You have the integer and then what follows the decimal points. So those two parts are separated by decimal points. Note, two parts separated by decimal points. So there's before the decimal points and there's after the decimal points. Good. So before the decimal points, we have the integer. That integer is called a characteristic, right? And that integer simply tells you how many times you can divide a number by 10. Do we get? Do we get? Do we get? So yeah, that integer, that's the characteristics, is basically it tells you the magnitude of the number. How many times can I divide this number by 10? So yeah, an example is given here. The number 456. 456 has a characteristic of 2 because you can divide it twice. Do you get? Right. If you divide 456 by 2 by 10, you get 4. If you divide the number 456, that's this. If you divide the number 456 by 10, the first thing you get is 45.6, right? Divide it again by 10, you get 4.56. 4.56 cannot be divided by 10 because it would not rank, so we don't count that. So 456 can only be divided by 10 fully twice. Do you get? Yeah, that's how you get the characteristic ideally. So yeah, we just see here 456, the characteristic is 2. Why? Because it's between 10 raised to the power 2 and 10 raised to the power 3. Yeah, that's just telling you that you cannot divide it by 10 twice. It won't reach the third time. So that means the value is between 10 raised to the power 2 and 10 raised to the power 3. Remember, the characteristic is not the log. There is an additional number. So this is just telling us that the characteristic and the additional number will fall in between 10 raised to the power 2 and 10 raised to the power 3. Yeah. So let's continue. You also have it for 4.56, 1. That's between 10 raised to the power 1 and 10 raised to the power 2. And then 4.56, 0, between 10 raised to the power 0 and 10 raised to the power 1. Yeah, so let's continue. The second part is called the mantissa. So, note, you have the characteristic and the mantissa. Characteristic, mantissa. Integer, decimal. Remember, 2 parts separated by the decimal points. Now, the mantissa is the one that is tricky. The characteristic was easy to get, was simple to get, was straightforward. Simply, how many times the number can be divided by 10? That's the characteristic. Now, the mantissa is the little bits, right, after 10 that is left. So, you divide the number twice by 10. That's obviously not it. That's not the end of it. There is the little number that is not after the decimal. That is the mantissa. Do you get? Now, this part is a tricky one that's not straightforward, but there is a way, a trick to be able to actually get it. And that is the trick that has been used to compute logarithms over the years. So yeah, let's find the characteristic. So, straightforward. Remember, like I said, once you finish with your research, you write an algorithm. The algorithm is what you translate into code, right? Research, algorithm, translate your algorithm into code. So yeah, we have an algorithm here. How does the algorithm work? Like I mentioned, first is to find the characteristic. You divide by 10, see how many times it goes. That's your characteristic. We start with the number 456. While the number is greater than or equals to 10, divide by 10, count plus or equals to 1. That's simple. While this number is greater than 10, so you have to ensure the number is not less than 10. So that's why 4.56 cannot count, because it is a number that is less than 10. So 10 cannot divide it in this case. So yeah, while this number is greater than 10, divide 10 by 10 and then add your counts. So this count plus equals to 1, it initializes the variable count and then it equates it to 1. Then for every iteration, it adds 1 to it. That's simply what that line of code is doing. So yeah, as we continue, well, number is greater than or equals to 10, divide by 10, count plus equals 1. So for every iteration, that's for every time this number is divisible by 10, 1 is added to count. So when we do 456 divided by 10, we get 45.6. Count is what? 1. So count is initialized as 1. Remember. Next, you take 45.6, you divide it by 10. What happens? You get 4.56. Count is incremented to 2. So count gets an additional 1. And then, why? Because it's on the second iteration, gets an additional 1. And then it becomes 2. Now, 4.56 is between 1 to 10. Do you get? So 4.5 is lesser than 10. That simply implies that it cannot be divisible by 10. Because of that, it doesn't work. We stop there. Right? The characteristic is simply 2 for 456. So yeah, straightforward. Like I said, the characteristic is very straightforward, very simple to get, and it's not difficult at all. Now, to the mantissa. So yes, to the mantissa. This is the side of things where it gets tricky, and I'm going to try as much as possible to take it slow. I'm going to try as much as possible to break it down as far as I can, as much as I can, because I believe once we understand the pattern to it, it becomes easier from there. So yeah, let's take it bit by bit. So we've established that the mantissa is the portion of the logarithm after the decimal point. So remember, the decimal point is the point of division between the characteristic and the mantissa. So the mantissa is the part after decimal points, right? So the key insight here is if log10 of x is equals to 0.abcdef, right? So abcdef is the mantissa, right? Then x will be 10 raised to the power of the mantissa. Do we get? Let me just go up so I can show you guys again from our definition of log x, right? Log 10 of x is 100, right, is equals to 2, right? That is because 10 raised to the power of 2 is 100, which means the mantissa here is 0.0000. So 10 raised to the power of 2.0000 is equals to our x. So simply put, 10 raised to the power of the characteristic and the mantissa is what? X. So yeah, this is just to make sure we understand this line. If log 10 of x is equals to 0.abcdef, then x is equals to 10 raised to the power of 0.abcdef. Yeah. So when we raise both sides to the power of 10, that means we do x raised to the power of 10, 10 raised to the power of 0.abcdef in brackets raised to the power of 10. Do we get? That's simply what we'll do here. Raise both sides to 10 beautifully, right? What we get is, because we are raising the 10 raised to the power of 0.abcdef to the power of 10, there is a decimal shift. It's like you are multiplying by 10, essentially, right? Because of that, there is a decimal shift to the left. Note, decimal shift to the left, which means that 0 goes, it becomes a point B, C, D, E, F. And that is very, very crucial, because we are still taking that. Remember, 0.abcdef is our logarithm itself, right? Now, when you raise that to the power of 10, that's 10 raised to the power 0.abcdef to the power of 10, that means you multiply by 10, there is a decimal shift to the left. What then happens is that a now becomes the characteristic. Do we get? A becomes the characteristic, B, C, D, E, F remain the mantissa. Do we get? So that is the old concept that powers the trick we want to use. Do we get? So let me go again. What you had before was x is equals to 10 raised to the power of 0.abcdef, right? You raise both sides to the power of 10. X raised to 10, 10 raised to the power of 0.abcdef raised to the power of 10. What does that mean? Essentially means you are multiplying by 10. Because of that, it becomes 10 raised to the power of a dot B, C, D, E, F. What I'm saying is a here was the first digit of the matriza. When you raise it to the power of 10, it becomes the characteristic because the decimal point shifts by one position. Do you get? Because of that decimal point shift, right? What happens is that A becomes the characteristic. Now, what do we say about the characteristic? We mentioned that the characteristic is the amount of times a number can be divided by 10, which means A here has now become the amount of times a certain number was divided by X. Do you get? A here has now become the amount of times a certain number was divided by 10. So A here is now the amount of times X was divided by 10. So yeah, what now happens is the integer part A appeared. It becomes the characteristic as I mentioned. We can extract out this digit. Do you get? And doing an inverse of that gets the initial digit. Don't worry, we understand now. We will understand. So yes. Yeah, as we were saying. Now, let's walk through finding the logarithm of 2. Log base 10 of 2. We know it's 0.301. It's easy to see, but we want to find it bit by bit. So yeah, we start by specifying that the temporary digit is 2. Why we are using a variable temp here is because we want to keep a copy of the original digit, right? So we just want to initialize a different variable. Let's just call that temp. It's temporary. So yeah, now for the first digit, that's we want to find how many times can we divide it by 10. So remember, when you do a logarithm of 2, it was 0.3 x prior. When we do the raising to power 10, right, what we get is 3 becomes a characteristic, right? Now, you now want to ask yourself, there is a number, like I mentioned, 3 becomes a characteristic. That means there was a number that was divided by 10 to give you the amount of times, which is 3. Do you get? Are we following? So this 3 here, like I said, that becomes the characteristic after you raise it to the power of 10, right, is there because a number X was divided by 10 3 times, right? So what we now want to reverse engineer is getting out said 3. Do you get? So we want to reverse engineer getting out this 3 by dividing that number by X. Now, you may wonder, how do we get this number? So follow me. So 2 is our X, right? We raise 2 to the power of 10. What do we get? 1024. Now, how many times can we divide 1024 by 10? That's all. So it's simply, we have our X. We raise our X to the power of 10. Remember, we are raising both sides here to the power of 10. So X raised to the power of 10 is equals to 10 raised to the power of a point B, C, D, E, F. That tells us what? This number that is now X raised to the power of 10 divided by 10, right? X times is equals to A. Do you get? Do you get? You know what? Let me take that again. We've established that A here is the characteristic, right? So if A is equals to 3, this is simply telling us that when you raise the power of X, when you raise X to the power of 10, if you divide that number, you can only divide that number by 10 3 times. So let's assume we do not know what A is. If we divide X raised to power 10 a number of times, we'll be able to get A. So let's say we divide 10. First time it works, second time it works, third time it works, fourth time it works. We will know that A will be equals to 4. But let's say it stops at 3, then we'll know that A is equals to 3. So yeah, I'm just trying to make sure you all understand the logic to the traditional logarithm calculator. Then we'll go into the code fully. Yeah, so yes, so we use that to find the first digit, right? That's that. Then this 1024, remember 2 was the starting point. We raised 2 to the power of 10 to get 1024. We divided that by 10. We saw that we can only divide it 3 times. That must mean A is what? 3. Chill? Good. Now, when we raise this again to the power of 10, that's this 1024 to another power of 10, you guys should remember, the next number, that is B, will now shift. It now becomes, B now becomes the characteristic, which means that I now have to check how many times can I divide 1024 raised to power 10 by 10. When I get that, that will tell me what the number B is. So, what do we do here? Remember, the temp is now 1.024 because we've divided it down to get 3. We've divided it down to get 3. We pick this up, we start again. Now, 1.024 raised to power 10, we get 1.267. It is not divisible by 10. Because of that, the second digit is 0. Right. We continue with our temp. Do we get? We raise that to 10. You get this. This is divisible by 10 one time. Then you continue that way. Do we get? That is the simple logic behind getting the Montesa of a logarithm. Right. And that's simply because there's a cycle of when you raise x to the power of 10, the Montesa shifts by 1 decimal point. And that's the perfect, that's a beautiful cycle. That's how we've been able to get traditional logarithm. That's how we've computed our logarithm tables over the years. Now, once we've gotten this pattern, this is the algorithm. Let's now move it into the form of code. Yeah, so follow me and let's go. Yeah, this is just an example. Log base 100456. First, you get the characteristic 2. That you can only divide 456 twice. Right? Now, when you divided 456 twice, you got this. 4.56 is now your temp. What do you now do? You raise 4.56 to the power of 10, and then you see how many times it can be divided by 10. When you do that, it gives you the first digit of the Montesa. So, you see how it's chill. Very, very easy. Yeah. So, and then you just continue with that cycle to get your orders. So, we are going to just take a look at, we are going to take a look at our code here. So first, we define our function. Function takes in the number and the precision. Basically, the number of decimal places you want to calculate, because can calculate it to infinity. So we stop at 6 decimal places. So yes, the argument, like we've mentioned, number to find the log 10 of, it has to be a positive number, and the number of decimal places to calculate, and it returns an approximate value of log base 10 of said number. Now first, we talked about error handling. We've mentioned that you want to anticipate the kind of errors that will happen, and you want to undo that. So yeah, if a number is less than 0 is given, like we mentioned, this only works for positive numbers. It has to be positive, and that is why we raise a value error stating that logarithm is only defined for positive numbers. That is our side of error handling. So yes, now that we've established our error handling, now we can get into the algorithm proper. The first step, like I said, when you have your algorithm, all you have to do is convert it to code. It makes your work very seamless and easy. It's why I always advise having an algorithm prior to you coding. So yeah, first is to finding the characteristic. Now, we have two sides. If the number is greater than or equals to 10, right, what do you simply do? You divide by 10 and you count how many times said number is divisible by 10 to obtain the characteristic. Sorted. We've mentioned that, we've given examples of that. Now, what of a case where the number is less than 1? Now we wonder, a number like 0.5, you can't possibly divide it by 10. How then do we get the characteristic? Easy. We simply count in the inverse. So for numbers now that were greater than 1, we could say that what we are trying to see is how many times they are divisible by 10. Right? For numbers less than 1, it's the inverse. You want to see how many times you can multiply it by 10 to get to greater than 1. Do we get? So a number like 0.5 now, if you simply multiply by 10, you get 5. So that means the characteristic is -1. But imagine a number like 0.05. You have to multiply by 10 twice to get your characteristic. So picture it like this. While a number such as 100, for example, you divide by 2, you divide by 10 twice to get 2. A number like 0.01, you'd have to multiply by 10 twice to get it between 1 and 10. Do you get? So numbers lesser than 1 are simply in the inverse. And that's because when you do it, what you have is 10 raised to the power of -1 or 10 raised to the power of -2. That's simply what you would see. Right. So for the characteristic now of 0.5, for example, the characteristic will be -1. That's because you have to multiply by 10 once to get beyond 1. So yeah, that is the way to understand, that's the pattern to get it. So yeah, now temp is between 1 and 10, which is what we want. We can then proceed to the next phase. Like I said, you want to get your temp to between 1 and 10, whether it was below 1 before, in the case of 0.5, you bring it to between 1 and 10, or it was above 10, where you divide it till it gets to between 1 and 10, and then you note down how many times it was divisible or how many times you multiplied as your characteristic. Good. Now, we've gotten the Montesa. Now, to the Montesa rather. When we did 456, right, the temp became 4.56. Temp here is the, when you divide it by 2, the last number you get, you got 4.56. The characteristic is 2 because 456 is only divided by 10 twice. Very simple, we've established that. To find the Montesa now, we raise 4.56 to the power of 10. Then we now see how many times we can divide that by 10 to get the first digit of the Montesa. Good. Now, we've established this K inside, we've talked about it. The Montesa is 0.0. The place, it keeps track of the decimal place, basically saying that this is the first digit, this is the second digit, this is the third digit. You have to keep track of the decimal place at which you are in. Now, for in range precision, basically, our precision, we've established that to be 6. So, in the range of 6 places, right? Remember, it's a cycle. You take the least divisible, the least, the number you got when you divide to the least, raise that to 10, divide by 10, so it's not divisible again. You take that, raise it to the power of 10, divide by 10, right? So it's a cycle of sorts. So we're going to repeat this cycle 6 times, at which point we'd have 6 different characteristics, 6 different decimal places, 6 different numbers beyond the decimal points. That's just the gist of it. So yeah, first the temp, right, raised to the power of 10, right? Then we count how many times we divide it by 10. Do we get? So what we have in our code here is, while temp is greater than or equal to 10, we want to establish that you divide by 10 and then you add to the digit. Do we get? This digit is then added to the Montesa at the correct decimal place. So we see how we are building up a string of Maltesers here. Do we get? Just by the algorithm we had previously established. So yeah, this is the beauty of having your algorithm first, then converting it to achieve something beautiful. So yeah, that is what we see here, that is what we have here. And at the end of everything, let me just rush because time is fast spent. At the end of everything, we combine our characteristic with the Malteser that we've built up. So yeah, let's just do a walkthrough. This is a code to show the walkthrough when we run the program. Then let's run the actual program. And yes, here we have a verification with the actual. So first, let's work with 2. Very simple. And then what do we see here? Example log₁₀, 2. You find the characteristic. 2 is between 1 and 10. You cannot divide it. So that means it's less than 10. 0. Because it's less than 10, right, it is the temp. So we take 2 as the temp here. 2 is our temp, right? We raise that to the power of 10. As you can see, 2 being the temp, raise it to the power of 10, you get 1024. Right? You then divide 1024 by 10. See how many times it is possible. That becomes the characteristics of the first number. So that characteristic, right, or the first one, you write it down. That is the first digit in your decimal place. Good. That is what we did here. You see, it's divided 3 times. The first digit in the decimal place becomes 0.3. Now the temp is now 1.04. You take that, raise it to the power of 10, you get 1.267. However, you can't divide by 10 because it's already less than 10. So our Malteser, in the second digit in our Malteser is what? 0. 0.30. 1.267. Now you've raised 1.267, which is the temp, to the power of 10. What do we get? 10.715 divisible by 10. Yes, you divide that, it's only possible once, which means the third digit in the Malteser is 1. Do you get? And that's how we get 0.301. And yeah, you see, final result log₁ with log base 10 of 2 is 0 plus 0.301, right? The integer plus the Malteser. And what do we get? 0.3101. Yeah, so when we did it extensively, this is what we got. This is the actual value. So if we also do the same for a number such as 0.5, right, what we see too is the log of 0.5 comes to negative 0.3012. So yes, this was a very, very fun project. I really enjoyed building this. It was just something to teach properly the rudiments of Python basics, which we have been going through in our AI and Data Science Bootcamp. So I just decided to share this and just have some discussions around it, especially on my channel too. So yes, please like and subscribe, and till we meet again, see you next time. Stay tuned to Moyin.dev. Beautiful things coming this way, beautiful projects that I'm going to be showcasing this new year. So yes, once again, thank you all for watching. Do have a great day.